What is Multipath Transmission Control Protocol? Mptcp is an ongoing effort of the Internet Engineering Task Force Multipath TCP working group that aims at allowing a transmission control protocol connection to use multipath to maximize resource usage and increase redundancy. Objective of the project created by us. The objective of our project is to improvise the performance of Mptcp networks. That is done by enriching the congestion control mechanism that emerges during the communication of multiple routes. Tools and technologies used for creating the project. The tools used for this project are Ubuntu. We had used Ubuntu for virtual operating system, in which we had implemented the NS3 software for simulation. NS3, also known as Network Simulator version 3, is a discrete event network simulator for Internet systems. C++ and Python programming languages are used for development of the code of our project. Working of Mptcp. The working mechanism of Mptcp depends upon the various mechanism through which data can southeast sent using multipath such as Wi-Fi and cellular networks. The congestion control mechanism is one of the mechanisms that controls the working of multipath simultaneously and improving the actual network performance, called throughput, which is core part of our project. Let us observe the actual network performance from the previous implementation, which uses the congestion control algorithms such as LTE, ALIA, BLIA and NURANO. We started from the basic research of Mptcp models named as Mptcp and NS3 simultaneously, and we analyzed how can we implement Mptcp in the Network Simulator 3, and this basic research was published by the Mptcp et al. In the above publication, the subflow management is done similar to Linux kernel implementation, and loss recovery is based on TCP NURANO, and this is purely simulation-based study. The result of this simulation-based study is generated on the basis of the NURANO congestion control algorithm. The results are here in Figure C. Figure A shows that Mptcp with the single flow, whereas Figure B here shows that the Mptcp with the two subflow. Figure C shows that the Mptcp with the single subflows and drop two packets. The throughput achieved by this implementation is shows here. In this picture we can see that the actual throughput is 99.6264 on the flow 1, where we can also see the throughput on the TCP flow 3 is 99.5991. This is because of the TCP NURANO congestion control algorithm, which have some issue of packets drops. The packets drop is one of the main issue in the Mptcp which need to be resolved. Many implementations showed different throughput and different ways to avoid this issue. As we discussed earlier, our concern is improving the performance of Mptcp, and this can be done by improving the congestion control algorithm, which control the congestion problem when multiple subflow are active. Since we are working on the Mptcp implementation in the Linux kernel, so here we are going to describe our third implementation of the Mptcp congestion control algorithm, whose name is DALIA Dynamic Linked Increase Algorithms. This is the recent publication which published in the March 2020, so we are currently working on this. We learned about the basic Mptcp implementation in the NS3 for the Linux kernel, so in our second implementation here we are going to discuss about the core part of our research named as Congestion Control Algorithm CCA, which is DALIA, so let's discuss about it. Since in 1986 the first ever congestion control failure detected by the internet when one end host transmitted more data to the other host, and in result unfortunately the router were unable to handle the extra traffic, resulting the packet losses occur. To handle this issue, Van Jacobson proposed the mechanism called as Congestion Control CC. The Mptcp connection consists of basic three elements, which are Path Manager, Congestion Control Algorithms and Scheduler. In the consideration of CCA, the single TCP path has three different categories such as loss-based, delay-based and hybrid, but here we find the loss-based only. MUET et al. Defined three design goals of Mptcp CCAS to ensure better performance and fairness over the internet. Multipath flow should perform at least as well as a single path flow would on the best of the paths available to it. This ensures that there is an incentive for deploying multipath. A multipath flow should not take up any more capacity on any one of its paths than if it was a single path flow using only that route. This guarantees that it will not unduly harm other flows. A multipath flow should move as much traffic as possible off its most congested paths, subject to meeting the first two goals. DLIA working. We propose a loss-based Mptcp CCA, namely dynamic DLIA, where rather than dividing the CWND into half after every packet loss event, we decrease the CWND by a factor which is dynamically determined based on the interval between packet loss events. Mathematical formula, where alpha is equals to for each loss event, we propose to decrease WR by multiplying by a decreasing factor, i.e., on per loss event on subflow R, where beta R is the decreasing factor bounded by beta minimum less than or equals to beta R less than or equals to beta maximum. We define beta R as where beta complement of R is the value of beta at the previous loss event, gamma is a balancing factor, and V is the ratio between the CWND at the previous loss event and the current loss event, and 0 is less than or equals to V is less than or equals to 1. If we define W complement of R as the CWND at the previous loss event, then we can define V as here, a large value of V near to 1 implies that loss events are occurring more frequently that require to reduce the CWND sharply. Performance and results. In these above figures, the network topology shows that the used for the emulations experiments. For performance evaluation of DLIA, we implemented it into the Linux kernel, and the result is shown in these figures. The performance of this DLIA CCA can be shown from the figure, which consists on the two subflows. The delays of packets on SF1 is 5 ms and path loss is 0.1%, and delays of packets on SF2 is 10 ms and path loss is 0.2%. This shows that subflows to create problems in the flow of packets, but we can see also in figure that single TCP path shows packets delays of 1 ms. In the figure B, we can see one single TCP connection and one multipath connection. So here in these scenarios, we neglected SF2, which created problem in the flow of packets. Here in this figure, we included 1 cubic CCA flow, which delays packets for 1 ms, whereas the multipath delays for the 5 ms and path loss is 0.1%. This shows that now the maximum delays of packets is 5 ms rather than the 10 ms. We can see the result of DLIA CCA according to the scenarios. There are two scenarios we discussed above in the figure 1. We can see the result of dynamic linked increase algorithm in the green spots in the above 3 images by considering the scenarios 1 and 2. Dynamic linked increase algorithms could successfully receive an average of 365 data, whereas LIA could receive only an average of 245 MB data. That was all about our project. Thank you.